Hi everyone, we are going to take a look at trigonometric identities. Now this is one of the most difficult concepts to grasp for all of trigonometry, but you will be looking at it quite a bit next year, so I wanted to introduce it to you at least. We should have done more of it this year, but we couldn't get to it. Same with trig equations. You're going to see more of that next year as well, so I wanted to make sure that you had an introduction to it. So trig identities, remember if we talk about an angle in standard position. So angle in standard position gives us our xy point and creates a right angle triangle with our x-axis with x and y. And remember, this is our radius and can be calculated r squared equals x squared plus y squared. Now, we talked about sine theta is equal to our y over our r, cos theta was equal to x over r, and tan theta is equal to y over x. And we're going to use that in the next step to demonstrate similarly. So if we now want to use this triangle, but we want what is called a rate triangle. So what we want is a radius of 1. Well, in order to do that, and I'm going to demonstrate it on this set of axes down here, that we're going to have to take what our radius was and divide by the radius to get a value of 1. And that means we're going to have a circle with a radius of 1, just to simplify what we have. Well, if we divide radius by r, we're also going to have to divide y by r and x by r as well. Just in similar triangles, dividing all of our sides by the same value. So now we notice that y over r is our sine theta, x over r is our cos theta, and now we have a radius of 1. We'll notice then that from our r squared equals x squared plus y squared, subbing in what we have here, 1 squared equals x squared, which is now our sine theta, and y squared, which is now our cos theta. Taking those out, sine theta times sine theta, and just writing it with the 1 at the end, gives us sine squared theta. Cos theta times cos theta gives us cos squared theta, and we have equal to 1. This is basically our most simplified trig identity. And this is what is called the Pythagorean identity, for exactly that reason that it comes from Pythagorean theorem. So, Pythagorean identity tells us that sine squared theta, and these simply come from our ratios, plus cos squared theta is equal to 1. And if we look at it the other way, we can figure out what sine squared theta is by taking our cos squared theta over to the other side. We can also isolate cos squared theta by taking our sine squared theta to the other side. So the big one to remember is our sine squared theta plus cos squared theta equals 1. And we must remember that. And we can use that and replace. So for example, we could replace sine squared theta with 1 minus cos squared theta. Those values are interchangeable, and we'll get into exactly why or how we want to use those in a moment. Now, if we also take a look at tan theta. So we want to be able to rewrite tan theta a little bit more simplified. So if we think about our sine theta from previous was y over r, cos theta was x over r, Well, if we take those and we divide them, so y over r divided by x over r, and we know that we rewrite that as y over r times r over x. Our r's cancel and is equal to y over x. Well, we saw this y over x in the previous slide that was equal to tan theta. So we can rewrite tan theta, if we want to simplify it with our basic functions, as sine theta over cos theta. And that's another one of our trig identities that those are interchangeable. Now, the reason that they're called identities is because they're true for any angle. So we could figure that out with a 60-degree angle, a 75-degree angle. The only one that it doesn't work for, obviously, when we're talking about tan theta equals sine theta over cos theta, is where cos theta is equal to 0. And if you remember where cos theta is equal to 0, if we start here and we use our function, so at 90 degrees and 270 degrees, cosine cos theta would be equal to 0. Well, then tan theta does not exist at that spot. And that makes sense because remember our original graph of y equals tan theta, we had undefined spots or vertical asymptotes at 90, 270, or pi over 2 and 3 pi over 2. So, whereas a linear equation is true for only a limited value of x, trig identities are true for any value of x or theta except for these ones. So demonstrating, and here you're just going to punch these into your calculator. So sine squared 30 or sine 30 squared plus cos 30 squared, and you can do that right in your calculator to demonstrate that. So 30 sine squared plus 30 cos squared, notice you get 1. If you put in a 90-degree angle, sine 90 squared plus cos 90 squared equals 1. And notice your calculator has to be in degrees for this one. Okay, so we're working with angles in degrees here. Your calculator must be in degrees to get the right answer. So those ones work even for 90 in this case because there is no denominator. So if we want to then prove that sine 60 over cos 60 equals tan 60, we're going to calculate sine 60 over cos 60, which gives us rounded 1.726. And then if we punch into our calculators tan 60, we get exactly the same answer. So we know that it does make sense. Tan of 60 is equal to sine of 60 over cos of 60. Now, same thing for our second one, sine 17 over cos 17. And again, rounding gives us 0.3057. And if we do our inverse tan this time, so let's do inverse tan of 0.3057, we get our 17 degrees. Okay, so either way we check it out, that does work, and that's going to work for every angle except for our 90 and our 270 within our first cycle. Now, also noting, if we know that tan theta equals cos theta over, or sine theta over cos theta. So if we know tan squared theta is equal to tan theta times tan theta, and we know tan theta is equal to sine theta over cos theta, then we know that multiplying our numerators gives us sine squared theta multiplying our denominators gives us cos squared theta. So we also know that tan squared theta is equal to sine squared theta over cos squared theta. Okay, so we can also use those interchangeable values. So if we want to prove an identity, means we want to take one side and show that it has to be equal to the other side. So we're going to take one side at a time and rearrange it, replace it with equal values or equal expressions to prove that they're equal. Now, in order to do that, following these techniques are going to help us. The first thing we're going to do is simplify anything that has a tan theta. So we want to get all of our expressions in our simplest ratios, which are sine and cos. So if we have a tan theta or a tan squared theta, we're going to rewrite them as cos or sine. Okay? Then we can also manipulate algebraically by factoring, expanding brackets, performing operations, common denominators. So we want to look at where we need to get to and how we're going to get there. So proving, a proof, as I said, is proving that they're equal. We do not ever move anything from one side to the other. We are working with one side at a time to find out if those expressions are in fact equal, or proving that they are equal. So notice that our right-hand side here is in sine theta. That is simple. There is nothing we can simplify there. So we're going to work with our left side, and we're going to specify that we're working with our left side. So first thing we're going to do, as we said, we want to simplify our tan theta first of all. And tan theta is equal to sine theta over cos theta, as we just talked about. And now we know that when we're going to multiply these, we can simplify diagonally. Cos thetas are going to cancel out, and that's just going to leave us with sine theta. Well, now we know we've proven that the left side is equal to the right side. We have proven that this is true. Now, for part B, we have 1 over sine x minus sine x equals cos x over tan x. Again, we're going to work with one side at a time. So first of all, we're going to work with our right side, because we have a tan x that hopefully we can simplify and get rid of here. Now we're going to rewrite this cos x divided by, and we're going to rewrite tan x as sine x over cos x, which we know we have to copy, flip, flip. So multiplying cos x over sine x. Well, now we can simplify this. Cos x times cos x gives us cos squared x over sine x. Well, in our left side, we notice that that only has signs. So what we want to do is simplify or get rid of our cos squared x if we can. Well, we talked about our Pythagorean identity that cos squared x is equal to 1 minus sine squared x over sine x. Now, at this point, maybe we're not sure how we can change this, but we notice that we have a single expression here. So maybe now we're going to go and we're going to work with the other side. And what we're going to do, because this only has a single expression here, we know that we can find a common denominator for our left side if we want to put that together. So we're going to have 1 over sine x, and we're going to multiply top and bottom. Remember, sine x is sine x over 1. So to get sine x in the denominator, we multiply top and bottom by sine x. We'll notice now we have a common denominator. We put those together and we have the same expression. So we can now say this is equal to the right side. We can say that this is equal to the left side. We've manipulated that data or that algebraically to show that they have to be equal. But notice we never move anything from side to side. Part C. This time we have sine cubed x plus sine x cos squared x equals sine x. So again, sine x over on our right-hand side is as simple as it will ever get. So we're going to work with our left-hand side. And what we notice is that there is a sine x. Notice our cubed x, we don't have any identities that work with that. We're not going to be able to replace that. But we notice that we do have a sine x in both of our terms. And because we know that on our right-hand side we have a single term, we're going to have to get to a single term. So we're going to common factor out our sine x out of both of those, which then gives us sine squared x plus cos squared x. And now we know that cos squared x plus sine squared x is equal to 1, which means that that has to be equal to sine x. Okay, so again, we've proven that that has to be the case. You just have to be careful of that you can actually do what you're trying to do. Okay, you can't just take something out and get rid of it. You have to follow BEDMAS still to make sure that you're doing the right steps. Part D, sine squared x over 1 minus cos x equals 1 plus cos x. So our right-hand side, again, doesn't have anything at this point to simplify. So we're going to look again at our left side. Now, our left side, we notice that our right side only has cos. So we want to look at what we have to get to figure out what we're going to start or where we're going to start. So cos x is the only ratio on the right-hand side. So we want to start by simplifying our sine squared x to cos squared x. And we know that sine squared x is equal to 1 minus cos squared x. Now we notice that we don't have a denominator in the right side. So we should be able to simplify and get rid of this denominator somehow. Well, if we take a look at 1 minus cos squared x, notice that that is a difference of squares. We have a perfect square at the beginning, perfect square at the end with a minus in between, which means we can factor it to 1 minus cos x times 1 plus cos x, all divided by 1 minus cos x. So because we now have the same expression on the top and bottom, we can reduce our fraction and it becomes 1 plus cos x, which means that it is equal to the right side, and we have proven that those two expressions are equal. Okay, now just remember we cannot cancel something in the numerator and denominator if it's added or subtracted to something else. We can only simplify if it is in its entirety a multiple. So 1 minus cos x over 1 minus cos x can cancel because they're not